We're going to look at direct proportionality as it applies to differential equations in this lesson. So first, let's remind ourselves what it means for two things to be directly proportional. And two things are directly proportional if one is a constant multiple of the other. So the mathy definition, y is directly proportional to x if there is a constant k such that y equals k times x, and we refer to k as the constant of proportionality. Sometimes that is explicitly given to you. Sometimes you have to figure out what that constant is. So let's look at it in the context of differential equations. And this is a very, very, very traditional setup. And this is very generic. A population, P of t, grows at a rate directly proportional. So there's the key phrase, grows at a rate, and the rate is directly proportional. So there's my key phrase there. And we are directly proportional to the population itself, or to the population size. They define k to be the constant of proportionality. And then we want to set up a differential equation that models this, and we'll solve the differential equation to get an equation for the actual population rather than the rate of change. So the grows at a rate is referring to p prime. However, in differential equations, I much prefer dp dt. So that's the change in population over time is directly proportional. So this sentence is saying that dp dt is directly proportional to the population size, and the population size is p of t. Now I'm going to shorten it to just p, but there is your differential equation. And now let's see what happens when we solve this. So this is not a lesson on separation and integration, so I'm going to do this very quickly. We'll divide by the p, we will multiply by the dt, and then when you do the antiderivatives of both sides, you get the natural log of p on the left side. And technically, that's in absolute values. However, population will be positive anyway, so we're not going to worry about those absolute values in a second. So there's your antiderivative. And then when you solve that for p, you get p equals e to the kt plus c. However, that plus c is often brought down in front through properties of exponents, and we write it as p equals ae to the kt. And at this point, you should be looking at that equation and thinking that that looks awfully familiar, because it should, because you beat these to death in pre-cal and probably in algebra 2 also. And you knew this equation down here, p equals ae to the kt, as the formula for uninhibited growth, exponential growth. And so that's really what we're looking at here. And now you see why the formula is what it is. This is also the same formula that you use for continuous compounding interest. So your PERT formula is derived the same way. So we're looking at that good old formula that you just kind of memorized last year, but now we have a reason for knowing that that is the population. And if you do remember from last year, that A value, that A is the initial amount. That is what you start with. So that's good to know when you are solving these problems, when you have more information to plug into it. So there is one application of direct proportionality with differential equations, and that's one you should have some familiar with based on your pre-cal knowledge. Let's look at another one, and this one you may not have seen. If you've taken a forensics class, you would have seen this probably, but it's Newton's law of cooling, and this is a simplified version because in the real world there's a lot more factors at play. But it basically says the temperature of a body changes at a rate directly proportional to the difference between the temperature of the body and its surroundings. And so no variables are defined here. I want to set this up. It does say the temperature changes. So we're talking about a change in temperature. So temperature changes sounds like dt, the change in temperature, over time. So we have to be careful with our t's, and I will define t to be the temperature of the body, whether it's a human body or a pizza sitting on the counter and cooling or whatever, but we'll let T be the temperature of the body. Changes at a rate proportional. So here we go. It is proportional, K, to the difference between the temperature of the body and its surroundings. So it's proportional to the difference between the temperature of the body and its surroundings. And so I need to define the temperature of the surroundings, and I'll just say R is the temperature of the surroundings, and I chose R because I'm going to call these surroundings the room that the body is sitting in. And so it's going to be proportional to T minus R. And in our situation for this video, we're going to assume that R is constant. It does not change. And so I'm going to make a note here that R is constant. Now, I mentioned earlier that this is a simplified version. In the real world, if you have a pizza sitting on a counter cooling off, the pizza is also changing the temperature of the room as it loses heat. We're going to ignore that phenomenon. We're going to assume the temperature of the room is constant for this case. So if we were to solve this through separation, I would divide by the t minus r. Whoops. And I would multiply by the dt. The antiderivative would give you natural log of t minus r is equal to kt plus c. When you solve that, you get t minus r is equal to e to the kt plus c, which is a e to the kt, which is the same one we had earlier. However, there's an r on the right side. R is a constant. I'm going to move that over, and we get the formula t is equal to r plus a e to the kt. And I do like to put that r before the a e to the kt. You can put it after if you want to, but I just think it looks better this way. So there is Newton's law of cooling in the context of differential equations. And then I just wanted to do one more example of a direct proportionality situation, only this time I'm giving you numbers to work with. So this will allow me to solve for a and k and r or anything else that applies to this problem. So we were talking about a population of fruit flies, and it says the population changes at a rate directly proportional to the number of fruit flies present. So the population, we have to define that. I'm going to call F, the population of fruit flies. The population of flies. We have T as time, and they do tell you T is measured in days. So the population changes. That's a reference to F prime, which will be dF dt. The population changes at a rate directly proportional. So K times something, and we are directly proportional to the number of fruit flies present, which is F. And here we have that same setup for exponential growth, uninhibited exponential growth. And this differential equation shows up enough that I think it's worth just remembering that the solution will be F equals a e to the kt. Let's cut out some of those steps with the separation and the integration. It will ultimately solve to that. Now, do remember, if you're an AP Calculus student, if this shows up on a free response question, you will need to show the little details on how you solve that. So don't skip to the solution if it's a free response question. However, multiple choice, which is where these problems typically fall, skip to the solution. So now let's start looking at the other information. There are initially 50 fruit flies. That is your initial amount. So I know that A is 50. So now I'm going to go down here and I will adjust my formula here. F equals 50 e to the kt. I still need to solve for k, and I can do that with this one. There are 125 fruit flies on day 5. So that tells me that F of 5 equals 125. So I could set that in over here. So 125 is going to equal 50 e to the k times 5. And if you solved that for k, which I did earlier, you get 0.183. So we'll do that in the calculator, and you get k equals 0.183. And so we now have a finalized version for my formula for fruit flies. I know that F of t is going to equal 50 e to the 0.183t. And the final question is, what is the number of fruit flies on day 18? And the reason I am finishing this problem, even though this is all pre-cal review, once I got to F equals a e to the kt, this became a pre-cal problem. I wanted to talk to you about the value of k and how important it is that you use the true value of k. If I plug in 0.183, like if I literally punch in 50 e to the 0.183 times 18, you will get a population of, where is it? 1,347.523. And because we were talking about living beings, I would round that up to 1,348 fruit flies, or you could truncate it, either one would probably be okay. And these are typically multiple choice, so you would choose whichever one they give you. However, I made a mistake there because I used a rounded value for k. K is not exactly 0.183. The actual value of k is 0.183 2, 5, 8, 1, 4, 6, 3, 7, 5, and it keeps going forever. We want to make sure we are guaranteed final accuracy or complete accuracy with our final answer. So what you need to do when you solve for K and you get K in the calculator, store it. I'm going to store this for, and I stored it in my calculator for K. You can store it for A, whatever. But if you store it and you find f of 18, we actually get a different answer. So f of 18 would be 50 e to the k times 18, and I'm using that stored value. And the answer you get when you do that is 153.799, which you could round up to, not 153, 1353, which would round up to 1354. So quite a big difference. In exponential situations, using a rounded intermediate value to get your final answer is exaggerated a lot more than in other situations. So please, please, please make sure that if it's a calculator active problem and you get a decimal for an intermediate step, you must store it to ensure that your final answer is accurate. So this one ended up being wrong. The correct answer is 1,354 flies, and there we go.